Um, Hello, everyone. In this talk, I'm going to introduce. I'm going to give an introduction to this young research domain, which is called the metasurface. You probably heard of this before or not, but today we are going to look into details. So, here's the structures. Like in the first part, I will wait. Okay, so sorry, but the computer seems to be stuck. So the thing is like here's the first part. We'll look at what is metasurface and what is the basic origin of this idea. Well, basically we will try to look back to a very basic concept, the Snell's law, and we will see a more generalized Snell's law. That is our starting point. And the second part, we will say how will this happen? I mean, how will metasurface manipulate light? Specifically, we will talk about four different ways to actually introduce the manipulation of light. In the final part, we will discuss where will metasurface go, namely what we are going to use this metasurface and what is the applications of this one. So let's first look at the light manipulation. Why would we want light manipulation? Well, you probably not noticed this, but actually manipulation actually happens in our daily life, and it's just manipulating light that can actually illuminate the worlds. Like for example, maybe like today when you wake up and you want to look into the mirror and say how beautiful or how handsome you are today, you will just need a mirror, and that's related to the reflection. And also, if you want to take an image in your camera, well, that probably need to related to the refraction, and it's like the light will pass through each lens, and that's where the manipulation happens. Some other things like the monitor, like some other fancy stuff like the AR display, anything like that. Well, the light manipulation not just happens in our daily life, it also happens in the research domain, where scientists can look into more details, like we can manipulate the phase, the amplitude, the polarization, and even the frequency, and so on. In this case, I mean, once we can fully control this, we can go into details. Like we can use our microscope to look into the details of the macro scale world, or we can use fibers to convert some large data and do some communication. Okay, so that's the reason why we want manipulate light. But so far most of the other components right now, just as I shown before, they are either bulky in size or they are not expensive, and it's hard to fabricate them. So here comes the motivation. Like, can we actually make a ultra thin, flat, light, and tunable other components, but they still have the full ability to manipulate light and achieve the same functions? The thing is, that is indeed the case. And this is a motivation why we want to use metasurface. The metasurface are some optically thin area of elements. I mean, when I talk about optical metasurface, so we can think of this as 2D array of some elements. Like in this case, there are some nanorods, and in this case, there are some nanobricks. So those are some sub-wavelength size and spacing, and we put them in a 2D surface, and by doing some manipulations, they can form the functionality we want to have. And next part, we want to say like how the light manipulation can be actually achieved. In order to say this, well, we need to revisit the reflection and the refraction theory. So let's consider a situation that a lifeguard wants to save a drowning man in the sea. So which path would this lifeguard take to save this man? Well, you probably will not take path A or path B, and you need to consider your speed and the path and the distance you travel between both the land and also the sea. So that is also the case for light travel. So according to the Fermat principle, the path taken by a ray between 2 points is actually the path that light can be traversed the least time, or more specifically saying that the path taken by a ray is a path that is stationary with respect to the variation of the path. Just as similar to this picture, where the navigator wants to consider both the distance and also the speed in the land and in the sea. Well, when light travels from position A to the position B, it also needs to consider this, but instead in optics, they need to consider the optic path, or like the accumulated phase when light is propagating. And by considering this, we can derive the Snell's law, which is related to the refraction and the reflection. I think you probably already know this equation in your high school or in your undergraduate course. But the thing is, like, only recent years, people started to look into this equation and found something more generalized Snell's law. Here we need to consider a different situation. Where again you are a navigator, but and you saw a drowning man in the sea. The difference is that there's a wall at the shore side. The height of the wall is actually varying, and at the left side it's higher, and at the right side it's gonna be lower. Do not ask me why there's a wall. Maybe someone called Trump built this wall. The thing is, like, in this situation, what would you do? I mean, when you want to save this drowning man, you also need to consider the time that you spent when you want to climb over this wall. In this case, you probably will not choose the original path this way. Instead, you will go a little bit further and climb over the wall here. This is exactly what light will do, because when there's a wall, you also need to consider the wall. And according to the Fermat principle, when there's a wall in the interface of two media, or in this case, I mean, when in the case of light propagating, the wall just corresponds to a phase, a gradient phase. As you can see in the interface of the two refractive index materials, there's gonna be a phase distribution or a gradient phase. And in this case, when we're calculating the optical path or the cumulative phase, we'll also need to consider the phase at the interface. So once we consider this, we will come to our conclusions and say that now if we look into the reflection or the refraction, we will say at the right side, they are not zero anymore. Instead, we need to consider the gradient of the phase, which means that we need to add an extra term. Well, maybe this is not straightforward. Let's think about how this could be influenced. Well, if we check these equations and we rethink the reflection and the refraction, we'll see that these situations can get different. We know that the incident light and the reflected light, they should be at the upper side of the normal line, where the normal line is just this dashed line, and this blue line is my incident light. However, if we add this extra term, we will see that the direction for reflection and refraction, they will be different. Since we need to add this extra term, so the reflection direction will actually point towards this direction instead of the original direction. And also for the refracted light, the light will pass and go through this way instead of this way. So in this case, the reflected light and the refracted light, they are at both sides of the normal line with respect to the incident line. This can be explained more illustratively using the Huygens principle, where it says that every point on the wavefront may be considered as a source of secondary spherical wavelengths. Those secondary spherical wavelengths together determine the wavefront at the next moment. And in this case, if you add a phase at the surface, you will see that for those secondary spherical wavelengths, you also need to add this extra phase. And when we check their wavefront, we will see that the light will actually go in this direction instead of the normal direction. Well, what's Well, if this is not very straightforward, you can consider a lens that made up of this type of gradient phase. And what you will see that is that if you look into the mirror, you cannot see yourself in the mirror because the light was reflected into some other directions. This means that if a friend stands by you, he or she can actually see you, but you cannot see yourself. This is something called the anonymous reflection and the refraction, and it was just derived and introduced in like 10 years ago. Okay. In this paper, they actually, let's think more about this gradient at the phase gradient at the interface. Like, what does this exactly mean? Okay, so we can look how the Maxwell explained the Snell's law. Well, we do not need those 4 equations. Instead, we just need 2 assumptions. Actually, not assumptions, but the facts. Like, the first one is a time translation invariance, which means that the frequency at 2 interference nature stays the same. The second is the interface translation invariance, which means that the transverse vector kx should always stay the same. Well, we only need those 2 conditions. And finally, we can get a Snell's law. So the things like the time translation invariance will not be broken, but people started to ask like why the interface needs to have translation invariance. I mean, why the interface needs to be uniform. The thing is, if we add just something like a phase gradient, the generalized Snell's law can appear automatically. And the interesting thing is that the Snell's law was introduced like 400 years ago, and it was only recent years people started to re-examine this law and looking into more details and looking in a more generalized way. And more interesting is that 2011 and 2012, 2 different groups, they independently came up with this idea from different in different ways, but they go to the same result. Okay. Well, since in optics, I mean, since like 2011, after that, a new domain just started, and people started to use different structures to introduce the gradient phase. And again, people start to ask, why do we need to use a gradient phase? Can we actually use some phase distributions instead of a gradient phase? Well, the answer is yes. And in fact, people have already done this. Well, I will take this as an example. Well, we not just think about the phase gradient, and when we think about the phase distribution, one example is one example we can rethink is what is a focusing length? Well, in terms of functionality, the focusing length is like when a plane wave comes in, they will be focused at a small spot. And this focusing length is actually very useful if you want to make a camera. Where in camera, there are actually many lenses. The thing is, if we check the from optics side, the thing is that when that comes in, a parabolic phase delay will be accumulated during light propagating through this focusing lens. And when that goes out, this parabolic phase delay would just means focusing spherical wave. Therefore, when light goes out from the focusing lens, they will just be focused. The thing is, since we can do gradient phase, why can we not introduce a phase distribution and make this type of phase distribution into a way such that they perform exactly like a focusing lens? The things, well, we can actually do this. And for example, if you arrange those metastructures in a way such that they're introduced a parabolic wave front or like phase shift or phase distribution, then when light travels through this 2D metasurface, the light will be focused. And this is just the case in this paper where it shows a metasurface that can focus light into 50 millimeter focal length. Okay, so in the first part, we introduced the idea of phase modulation, where we mentioned that if we add a phase, then we can manipulate the light propagating, either like adding a phase gradient or adding a phase distribution. So the second question you might want to ask is like, how can we introduce this phase in the 2D surface? Well, there are actually many ways, and it can be divided using different materials. To begin with, people are using the metal, since metal usually can have like can either have a electric response or have a magnetic response. So, but metal can actually have loss. So most people started to use dielectric layers, which based on the propagation phase or even the geometry phase. So this means that there are actually 4 different ways to introduce the phase. I will not talk all of them in detail, but instead I will focus on the first paper where they use this phase-shaped antenna to introduce the phase discontinuous. So we're talking about the phase-shaped antenna. We will talk about the resonance of single strip antenna first. Things like if suppose that this is your antenna, this is your strict antenna, and when the incident light is polarized in this direction, you will see that at different wavelengths, the resonance conditions will be different. And specifically, when you change your wavelength lambda, you will see that your first order resonance will happen when the wavelength is around twice the length of the antenna, where L is just the length of the antenna. And if you look at the phase and also scattered electric field, you will see that at the resonance, a large phase shift and a strong scattering cross section will be introduced. This means that if you look from another way, that means if we change the length of the strip antenna, we can see that the resonance wavelengths will be shifted. Like we can see apparently the lengths of the antenna are different, and the peak of the scattering are shifted according to the length of the antenna, which is good because by just changing the structure of the antenna, we will be able to somehow introduce a different phase because the resonance conditions are different. So we should expect a different phase. However, the thing is, like if we just use a single strip antenna, you will never get a 2π phase shift, because if you look at here, the maximum phase shift is just pi. And in order to fully control the phase, we actually need a 2π phase. So what people did is like they combine 2 antennas together and they form something looks like this, where it's like a V-shaped antenna. In this case, there are actually 2 modes. The first mode is the symmetry mode, where the light is polarized along the center of those 2 antenna. You will see that the electrons will move from the center to the endpoint. And in this case, the resonance wavelength is actually twice the length of the antenna, whereas the H is just the length of the single antenna. The second type of mode is the anti-symmetry mode, where in this case, the light is polarized along this direction, so that the electrons will move from this endpoint to this endpoint. So that in this case, the resonance wavelengths will be 4th the length of the antenna. And since we can always decompose the instant electric field along the symmetric direction or the anti-symmetric direction, we can say that we can actually add those 2 modes together and expand the modulated phase to 2π. This is what they actually did in the first paper. By changing the length of the antenna and also by changing the orientation angle or the opening angle, you will see that the phase introduced in each antenna will be different. And in this case, they form a type of gradient phase. So what people usually did is like, they first change these nanostructures in terms of the length h or the opening angle delta. You can see that here, right? And you do a simulation and you figure out what their phase is and also what their transmitted amplitude should be. So in order to like have the specific phase modulation you want, you can just pick any phase you have in this table. For example, in this picture, they pick those four different structures, and they can either form this type of gradient phase, or they can either form this type of phase distribution, and this is used to generate the vortex beam. Some other things used in metal is like the gap plasma-based tandem. I will not look into this in detail. The structure looks like this, where they have a metal brick, and there's a dielectric layer, and in the bottom it's also a metal film. And the thing is, like, if you change the structure, which is the length of Lx or Ly, you can see that we can also manipulate, we can also modulate the transmitted phase or the reflected amplitude in this way. Some other things like the waveguide based, this is like they are using dielectric layer. Sorry, they're using dielectric materials, since metal can always introduce some noise. So the waveguide introduce propagation phase says that if we consider a very non-rectangular dielectric unit cell, then we can treat this as a waveguide. Since my structure, I mean the structure of the rectangular dielectric part, I mean the length L and the width W, they are different. So basically, like for TE mode or TM mode, they will have different phase shift, and this can be used to modulate the phase, the propagating phase. Another type is called the geometric phase, where it says that in the anisotropic media, an actual phase delay will be introduced. And the interesting thing is, like, if you use this geometric phase, you do not need to change your structure, but instead you can just rotate your structure, and boom, you will get different phase. Okay, after I introduce the phase, introduce some general ways to introduce the phase to this material, to the surface. The general way is like you can change the structure. For example, like the width, the length, or the shape, and even you can rotate the structures. That's the way how you introduce the phase. However, what are we going to use this to do? Which means that what is the usage of this? Well, we can. Well, the thing is, like, we can use this to manipulate the phase, right? Well, before we do this, we might need to consider the mathematical expression of the light, and we need to think about which part we can modulate. The most straightforward way is like the exponential term, which corresponds to the phase. We know that the phi is a phase, right? And the k corresponds to the propagation direction. Usually those two are correlated with each other. And by modulating the phase, what you can do is like, well, you can generate a beam deflector, which means that you can like engineering the direction of the light so that they can point to any directions you want. The second is like the metalens. I will mention this in detail later. And also you can do this with hologram or angular or like augular angular momentum generation. Well, what you can do, well, if you write a mathematical expression in this way, you'll see that there's actually some other terms we can modulate. For example, we can modulate this A, which corresponds to the amplitude. What we can do is like we can make a material, make a surface that can either totally absorb the incident light or totally reflect the incident light. Or another very useful domain is called the structural corner. Well, I will also mention this later. Another thing you can also modulate or manipulate is the E, which corresponds to polarization. You can do something sort of like a wave plate or vector beam generation, or you can either like detect those polarizations or like image the polarizations. And overall, there are many manipulations you can do, not just the phase, but many parts. And this is just in the space domain. I will later mention what we can manipulate in the time domain. Okay, so in the first part, we will look at the metalens. As I mentioned before, the focus length is just like a parabolic phase delay. So we can actually introduce this phase profile in a 2D surface. And once we have this phase profile, where you see that the F is my desired focal length, the X, Y is a coordinate for my net surface, and the lambda is my incident wavelength. So what we have is like, once you have this phase distribution or phase profile, in each coordinate, you can have the desired phase, right? Then you just pick from the table we have before. Like you create a table in terms of the structures, like in terms of the height, in terms of the width, in terms of like different shapes, anything like that. And you just pick the desired phase and you put that in that coordinate. And you can do the same thing like this. And finally, like if you put all those structures in the same in this way, you can finally form a thing called metalens. This is what the metalens looks like, and this picture shows an illustrative way for the light to be focused. And this is focusing ability demonstrated by this metalens. Well, you can also, you can also use this to do some imaging. Well, this is like demonstration that they can use this lens to image a very small structure. Since, some other lenses, like some other things we can check is in the metalenses, like we can do a achromatic metalens. What does achromatic means is that every different, when the light is different, when the incident light is different wavelengths, they can always focus on the same spot. Because of dispersion, the introduced parabolic phase will have different focal spot corresponds to different wavelengths. Therefore, we need to compensate for that dispersion, since we do not want the different color to be focused, different wavelengths to be focused at different spots. And this can be solved using metalens, because you can always introduce some more complicated structures so that they can actually compensate for different wavelengths, so that they have a focusing wavefront for different lengths, and they will be focused at the same spot. This is what it looks like. Another thing you can do is like, well, if you have a camera, you will see that most camera you can change the wavelengths, right? We can also do this using metalens. The thing is like, well, if you put this structures in some stretchable materials and apply this voltage, you will see that by changing the voltage, the focal length will be changed, and this can be realized for some like variable focal lengths. Well, those two are just some. Well, you might say that this can be realized using some traditional optical components, right? But those two are some other things that cannot be realized. For example, you can do some focusing in terms of polarization. For example, you can, if T polarized light comes in, they can be focused into the left side. And if TM polarized light comes in, they can focus to the right side or reverse. Another thing is like the image edge detection, which means that if you send me an image, I cannot, well, I will not just give you an image, but instead I'll give you the edge. And I actually did an image edge detection. This is going to be very useful for some medical applications like the tissue or organ imaging. And another type is a hologram. Application is a hologram, as you can see here. Well, you might probably only see this in some scientific fiction films. However, we can also realize this using this Metasurface. Basically, if you want to create a hologram, you can just inverse compute what the phase profile should be in order to generate this type of hologram. And later on, based on what I described before, if you have a phase distribution, then you just put each structures in that coordinate corresponds to each each phase, and boom, again you will have the hologram image. Some other things people could do is like the multiplexed hologram, which means that in one figure I can generate multiple holograms, and if the light is incident in different conditions, like if they are in different polarizations, they will show different image, or like if they are in different hexanality, which means like the left polarized or right polarized, you will still see different image, or like wavelength multiplex hologram. Another useful hologram is a conical hologram, which means that by designing the metasurface, you can actually see a conical image, which is very close to our real image. And yeah, and the second thing I will talk about is the structural color. Well, in terms of the color, we might need to think about what is the origin of the color in nature. So there are actually two types of colors in nature. The first one is comes from the absorption of the pigment. We know that, and like this. Well, you might have like carnival clothes or carnival books or anything like that. They might, I think they might use this pigment. However, one disadvantage is that the pigment, they usually fades after several years or longer time, and they usually have a low resolution. And the second type of color is called a structural color. We can actually find this in some animals like the peacock or the butterfly. If you look at the peacock or the butterfly more closely, you will see that they are actually made some like nanostructures. So the things like when light interact with those certain nanostructures, and they got some interactions, they will have different reflection spectrum, and in that case, will show certain color. The thing is like if you notice this, you can also make nanostructures that behaves like this way, and then we can get the color we want. Again, we can either use metal, like by building up this nano rods, and by change this diameter or the gap between each nanorods, we'll be able to see different color as shown here. Those are just some examples of the image. And or you can use the dielectric materials like the silicon to build out this nanorods. I mean, you can still see those colors. The advantage is that using this nanostructures, they will never fade, and they will actually have a very high resolution, since you see that, I mean, those are in like tens of micrometers. So you can actually get these colors in a very, very small size. Well, okay, and then let's go to the next part. All the things we talked about before is based on the space domain manipulation. But we can also manipulate light in a time domain, like the pulse shaping. Well, if you, for example, like if you give me an instant pulse that looks like this way, and after the light goes through this metasurface, we expect that light can behave something different, like this way. Well, how can we manipulate light in the time domain? The things, well, we can just, this is like equivalent in manipulating this in the frequency domain. So we first like using some type of gradients so that the light can be decomposed into multiple wavelengths, and later on in each wavelength, you just manipulate the amplitude or manipulate the phase, and finally, you just like combine all of that together, and in the time domain, you will be able to see that the light will actually change. The shape of the light actually is changed. Well, what I talked about before is actually like the metasurface is a fast developing domain, and there have many other applications. And in the recent 2 or 3 years, people have started to look at their other applications. For example, since most of the nanostructures, they have some type of strong magnetic or electrical resonance, so they're very sensitive to the environment change, and they can be used to either detect, do some bio imaging or sensing, or you can combine this with some 2D materials and research into their interactions. Or another type of that's very hot recent years is computational metasurface, and especially a new domain called the inverse design have already emerged. Since well, their basic idea is like this. Well, in order to design a metasurface that has specific phase, what you need to do is that you need to scan those structures and find the specific phase. However, this can be done using some machine learning techniques, and people have already done this and have some very good results recently. Okay, so I think that's gonna be the end of my talk. And there's some takeaway message. The metasurfaces are some 2D structures with the subwavelength size, and in each structure, the structure itself can modulate the phase so that the metasurface can, in the surface, they can actually modulate the phase distribution and more advanced modulation so that the metasurface can manipulate light and exhibit the multiple functions. And finally, yeah, that's going to be the last page. And thank you for your attention.
Thank you so much for the wonderful talk. I'm going to end the recording and open up the floor for any